So you were saying you recognize this dude from the video? You recognize him? Remember the video the first day? Who is this? What? Euclid? Euclid? Euclid. Euclid is the guy you have to thank for sitting here today. Euclidean geometry. And it's not like he invented this stuff, but he kind of wrote it down. He invented a method, like the mathematical way of looking at things. Yeah?
Is there any other kind of geometry?
Yes, there's all kinds of geometries. Yes, the short answer to that question, yes. But Euclidean geometry is what we're going to be looking at. And he took stuff that people knew about, but he wrote it down, and he made it kind of for real. He made you have to study it. He introduced this idea of mathematical rigor. And what math is based on is a set of assumed principles. You have some undefined terms, axiom and postulates. I'll tell you more about that in a minute. And they serve as a starting point for proving other statements. So it's like you minimize the number of assumptions you have. So you have a bunch of assumptions. And you try to minimize this. And then based on these assumptions, you prove some new facts. And you don't prove them inductively. How are you going to prove them? Deductively. So, very strong ones. So that these new facts are very strong. Now, what's the weak link here? So these are all proven. Isn't that great? So what could be the problem? So if your assumptions here, if you find a problem with one of your assumptions, what happens to your whole world of mathematical facts? Yeah, what happens? I'm sorry, Amanda, did you want to say something?
It's all, it could all be proven false.
Yeah, or something. We don't know. We can't really say that this is strong anymore if we find problems. So that's why we try to minimize the number of assumptions. And we try to make sure they're really pretty sure that they're true before that. And that's what math is based on. So we start with an undefined term. And undefined term, part of this is what's a definition. And math actually has a very strong, I won't say definition of definitions, but that doesn't sound right. But there's a format. For example, if you want to give the definition of a Siamese cat, you would say a Siamese cat is a cat. Let me just say, I gotta have to remember these. So what's a Siamese cat? So the first thing you say, a Siamese cat, the thing you're defining, is, and then you say what bigger categories it belong to. It's a cat. And then you say what's different about the Siamese cat as opposed to the regular cat. It's a Siamese cat that has points on its nose, tail, ears, and legs. So basically what you say is, here's the new thing I'm defining. What category does it belong to? And what's different about it than other things in that category? That's a formal definition. Yeah. Well, if you look at my little, somebody made a picture of my cat over there, my late great cat. He was Siamese. So he's got those points. And that's what they're brown, but they're, difficult points. So anyway, that's a formal definition. The problem is, well, you need some kind of category to start with. So we're going to start with some undefined terms that we can use to build definitions on. Our first undefined term is a point. Now you know what a point is, right? What's a point? What's a point? Amanda, what is that?
Why does no size dimension but represents the location? We never look at that with a letter.
You know what? I could not have said that better myself.
Yeah, you did.
Oh, because I did say that. Oh, that's what it says on the paper. Smart girl, she got me. So it has no size or dimension. Now, what does that even mean, no size or dimension? It's very hard to even think about what that is, Jack. Like, what does that mean?
It's just a point in space.
Yeah, it's like a location. It's just a location. But even though, we tend to make a point, here's a point, and that's point P, and we name it with like an uppercase letter. This looks like it has size. It doesn't. It's just a precise location. 0 dimensions. It has no dimensions. And that's a very hard thing for us to comprehend. Now, our next undefined term is the line. And you all know what a line is too, without reading my little note there, right? You've all seen lines. Here's the formal definition of it. It has no thickness. Now, I've drawn a line here. It looks like it has a thickness, but it doesn't. It's the location of some points. Now we have a dimension. We have one dimension to it. Okay? So it has like length and width here, right? It's just length, actually. I'm sorry, it just has length. That's its dimension. And it extends infinitely in both directions, which is why these arrowheads here are extremely important. Now, I was looking at some of the, I'm trying to think, I think I had you graph lines on our diagnostic. I can't remember if it was this one or the alpha one. And people were graphing lines real nice, but they said, here's my line. And I'm a stickler, I'm like, no, it's not. You have to put these arrows on. You haven't graphed it unless you show me every point. And that's what these arrows mean. That's important. Because it goes infinitely in both directions. You name them, you pick 2 points on the line, and you give them the names, and then the way we name it is we just say line AB, and this little symbol on top looks like a little mini line. That tells me AB is a line. And it does have to have the little arrows on top if you are naming a line. And through any 2 points, you can fit exactly one line. Any 2 points, you define a line. All right, and now our third undefined term is a plane. Now a plane, it's kind of like a piece of paper, but it extends infinitely in all directions. And I guess it's really hard to like make this have arrows like you do a line. But it is understood that planes go infinitely in direction. Now this is a 2-dimensional thing because it goes this way and it goes this way, but no thickness here. So it's a piece of paper with no thickness. It's hard to imagine it. Yeah.
It doesn't always have to be parallelogram.
No, it's not a parallelogram at all because this extends, and it never ends. So there's no edge. There's no edge. And yeah, it's like you really got to think abstractly here. We can't draw that, right? And there's no way for me to draw something with no end. So in our mind, we have to kind of realize this extends forever, this extends forever, in all directions it's extending forever. And that, it can blow your mind a little bit.
It's like a universe.
Well, kind of, except the universe curves, right? Now in our plane...
The universe does curve?
I believe Mr. Einstein, Dr. Einstein told us that. Well, it curves.
Does the universe ever end?
Oh, please.
Yes, it does.
What do I look like? Stephen Hawking? No.
If you ever get to change, what happens?
You can't get into the end. You can't get to the end. It's impossible to travel faster than the speed of light in the universe. Never expanding at the speed of light.
Hey Jack, what happens if you're driving your car at the speed of light and turn the lights on? I've always wondered. Oh, come on.
You can't turn the
Oh,
speed of light.
come on. I have to credit that comedian now. I can't think of his name for a second. But yeah. Yeah. Yeah, I don't know. I don't know what happens. All right, back to this.
Will you see the light by streaming?
So, it extends infinitely. Now, how do you define? Now, you define a line by 2 points. You define a plane by 3 points, except this word in red is extremely important. Let's see if we can figure out what this word means. Non-collinear. Let's break it down. What does linear mean? What does linear mean? Amanda?
It means that just the line.
Yes. Now, what do you think collinear means? Joseph, what's collinear? I didn't hear that at all, but okay. It's on the same line. They're co-points on the same line, and then it's non-collinear. So what does that mean? What does that mean? What does that mean, Julie? Well, they're not on the same line. So 3 points not on the same line, because if it's 3 points on the same line, you have a line. Now see, right, this is a line, but if I put a point up here not on the line, see I can lay a piece of paper on top of that? You get your plane. So any three non-collinear points, if you kind of picture the plane around it. So very important, non-collinear. It says here named by 3 points or a lowercase letter. So you can say this is plane ABC, because they're not collinear points. Notice here it says lowercase, so it's not lowercase. It doesn't really have to be lowercase. Most often I see them in cursive, like this is plane M. But you get the idea. If they didn't draw a little point next to it, they mean this is plane M. So you can use one letter to name it or 3 different ones. And I forgot to mention up here, this is line AB with these points, but it's also line L. That's a little hard to read. That's a lowercase letter. You can use a lowercase letter to name a line as well. Alrighty. Now we can get to defined terms, because we do have some undefined terms now. What's a segment? Okay, I don't have the real definition, but a segment is a line with two endpoints. So it's like you start with a line, but then I make two endpoints to it. Okay, so, and it's all the points in between. So this is a segment. How do we name this? It's still called AB. Now when I put my line on top, this time I'm not putting the arrows. And that tells me it's a segment and not a line. So the little arrows, they change the meaning whether they're there or not. That's why it's important. Yeah.
They wouldn't have quotes again, like.
Here they are.
AB, no, I mean, on top of the AB, it's just like a little.
A and B are the points.
No, I mean, like, on top of if you wanna name it, would there be points on that line?
Oh, you could, but it's understood if you don't. If you just put a straight line across, that's good enough. No arrow, I get it. All right. The other thing we've got is array. An array, it's a line with one endpoint. A line with one endpoint. Okay, so array AB, and look how I'm naming AB. Now this order matters. To name array, you start with the endpoint, and you pick another point on your array, and then look where my arrow goes. It's one-ended arrow. So no arrow here, and just that there, array AB. And A has to be the endpoint. Yeah?
Well, if it's just like a ray, like from the bottom.
Yeah.
Would the arrow be facing the
Nope, nope. Your arrow always goes this way, so how would I name this ray over here? BA. You see what we're doing there? It's like, here's your endpoint, start here, take another point on the line. You're always going to have them look this way. It's a great question, glad you asked that. Okay, so that's a ray. Now, opposite rays are rays with a common endpoint, but they face an opposite direction. So here is my line AB. So it's a line, it's hard to see, there are arrows here. And CA, ray CA, again, that always goes there, and ray CB are opposite rays. They have the same endpoints, but and there all have to be collinear points here, and it goes in the opposite direction. So they have to be on the same line, same endpoint going in opposite direction. Opposite rays are collinear, same endpoint. Questions? Pretty much here's what it is. Okay, so let's make sure we can name all these things. So it's very hard to draw a three-dimensional figure because we've got this line kind of sticking up out of the plane. Very often you'll see the dashed lines meaning it's behind the plane. And we're using our X-ray vision to kind of see it there. So let's see, we're looking at line EF. So, I'm just trying to do, not on here. Okay, not on here, that's fine. So line, give another name for line EF. Here's line EF. What's another way I can name this line? Keely? Yeah, this is line N. So I'm using line N. Can you name 3 points that are collinear on the same line? Julia? Yeah, C, B, and D are all collinear. They're on the same line. Name 4 points that are coplanar. So what do you think coplanar means? On the same plane, right? So what do you think, Joseph?
D, C, E,
Okay, that works. All right, 4 points, they're coplanar. Give another name for segment EF. I don't even need this word segment, but I can see it's segment EF. That's right here. What's another way I can name segment EF? Amanda?
Segment of E.
Yeah. Does order matter for a segment? No. When does order matter for array? Name array with endpoint E that's an opposite ray to EC. That's an opposite ray to EC. So here's ray EC. What's an opposite ray? ED. Please put your book away. Okay? Get it? Intersections. So let's see. 2 or more geometric shapes intersect if they have 1 or more points in common. So here's an example of intersecting lines, kind of in the middle-ish of the page now. The intersection of two lines is they intersect where? What kind of place? This is not meant to be a trick question. Yeah? At points. Yeah, that's all I'm looking for. The two lines will intersect at a point. On the other hand, two planes are intersecting. Where do they intersect? Jacob? At a line. So two planes are intersecting at this line point. Let's picture, I don't know, two papers kind of intersecting together. Yeah?
So it's sort of like, if you were kind of like, put it in order, it would be point line plane.
Kind of, because one has 0 dimensions, one has 2 dimensions, 1 dimension and the other has 2 dimensions.
So whenever they two get intersected in one point, like.
Well, now you're just gonna blow my mind here, because what happens now when you have things that are more than 3 dimensions and, yeah, I know, it starts getting really complicated. It does. All right, well, let's see if we can name these intersections. Name the intersection of line KL and line PQ. Now I gotta find it. So here's line KL. Oh, goodness. And here's line PQ. Jacob, what do you think? Point J. That was about right. Then we have to name the intersection of plane R. This is plane R, right? And this plane here. And the other plane S, which is this one. So we have to name the intersection. What's the intersection of that going to be? What do you think, Ellie? Line and N. Okay, I have to put my little line symbol across the top. That shows that I know it's a line. Let's see if we can name 3 pairs. Okay, 3 pairs of opposite rays. Give me one pair. Somebody give me a pair of opposite rays. You got one, Evan?
JL.
J. Okay, so JL and JK. Good. We named them correctly. Start with the endpoint and give another point on the line. So there's one of them. He identified this one here, these, and this. All right. I need another set of rays, opposite rays. Joseph, you have them?
JQ.
JQ and JP. And that's here. And we're going to call it this one and this one. And then do we have any other opposite rays? Amy? JM and JN. These are rays. And let's go over here. Awesome. Okay. Not too tough, right? Other questions? Yeah?
So is line NN the only one that you can put down, or could you put down the other?
Do you see any other lines where these two planes are intersecting? And you can think about maybe 2 pieces of paper, and you kind of cut a slot in one, you kind of put it through. Like, do they intersect anywhere else but at one line? It's kind of like if you have 2 lines, can they intersect at more than one point? No, and if you have 2 planes, which I'm not really drawing. So here's one plane. I'm trying to kind of draw another plane. Like they intersected. I can't get another line in there. That's it. One place.
Oh.
Yeah, I know, they're hard to see. And I will say this, there used to be a time, like I know when I went to school, you couldn't take geometry before 10th grade. And the reason they did that was because people's spatial and visual spatial skills develop at different rates. And when you're about 12, 13, 14 years old, you don't necessarily have it developed yet. There are some people that look at this and they cannot see that 3D shape that they're trying to represent here. If it's you, don't feel that at all. You will be able to. But that used to be the reason why they waited for geometry. Now they're like, oh, well, too bad. So you're just going to have to cope with it. But trust me, there is a 3D kind of figure here that you may not be ready to see yet. But if you don't see it yet, you will someday. All right, now we talked a little bit about what we're building all these things on. Definitions, so these are definitions we can use to build new rules, new theorems. But now we've got all these words: axiom, postulate, conjecture, theorem. Now I know you know what a conjecture is, right? We've talked that to death. So a conjecture, right, that is an observation you make and you make a statement out of it, usually in if-then form. It doesn't necessarily have to be. but usually. So it's a statement that we, not proven false, and it's not proven true either. So it's an unproven kind of a statement. That's a conjecture. An axiom is a statement that we haven't proved, but it's obviously true. Whatever that means, right? And that was Euclid speaking. That's an axiom. It's obviously true. It's an assumption. These are assumptions he used. Postulates are a very similar idea. They're also not proven. They are assumed true. Very subtle difference between these two words, axiom and postulate. We're basically going to use, as we use them, they're going to mean the same thing. That they're unproven statements that we can use in proofs. There's a slight difference. Don't worry about the difference. One's an axiom, one's a postulate. They're just things that are given to us as assumed true. Now, a theorem, on the other hand, is something we have proven true. So basically, you take a conjecture, you use axiom, postulates, and other theorems to get new theorems, and now I have a new fact. So theorems are proven, and you can use theorems to prove other theorems. You can use axioms, postulates also. You can use definitions. So we use these and definitions to deductively prove new theorems. So it's a little bit of a house of cards, because if for some reason our assumptions are bad, the whole house of cards can fall. But so we're very careful about what we put here and what we assume and what we don't assume. So we limit what we put here. Yes, Amanda?
By the way, I know theorem is this little math word for fact. Is there a math word for like a lie that is proven false?
I don't know of any. I don't know. Maybe there is. I don't know that answers that question. I only know what I guess we're focusing on truth more than falseness, but maybe there is. There probably is. Maybe you can Google that for me. See if you can find out, because I would like to know. All right, so we're going to start with postulate number 1. All right, postulate number 1. We're on the back now. Postulate number 1 is called the ruler postulate. Now remember, postulates are things that we're assuming are true. We're not going to prove them, but we're assuming they're true. And again, these are not quite the axiom level, which are obviously true. These are, we think, we're pretty sure. So here it is. The points on a line can be matched 1-to-1 with real numbers. So if you think of a ruler, right, it's got little numbers on it, and we're matching points up to it. So the real number that corresponds to a point is the coordinate of the point. So we're basically defining a coordinate system. The distance between points A and B. All right, let me go here first. So it's like you have a line here, and I'm just going to put numbers in. And so now these points have numbers associated with them. I could put numbers in between numbers, right? And there's an implied length or distance between points. So what would the length be between 5 and 6? What's that distance? It's not a trick question. What, 1, thank you. What's the distance between 4 and 6? What's the distance between 1 and 6? That's my, I'll put something here. What's the distance between 1 and 7? 1 and 7? 6. Isn't it? 1, 2, 3, 4, 5. Right? So, how do you get that then? What are we doing here? Yeah, what are we doing here, Joseph? We're subtracting it, right? So this basically says you can find the distance between 2 points using subtraction. Now the only problem is, what if I did 4 minus 6 instead of 6 minus 4? I could, right? And then I get negative 2. Well, that's not a distance. So we say distance is a magnitude. It's you know, something. Yeah, so you use absolute value. So this thing here, it's just saying if you have points x1 and x2, subtract them, take the absolute value, you've got distance. So it looks complicated, but it's not. Assign a number here. If this was 3 and this was 6, what's the distance? Well, subtract the 2 numbers and take the absolute value. Just in case you did 3 minus 6. So we just want to make sure you're always taking the positive value. Yeah?
So in a postulate, I wouldn't have a theorem.
Sure, if you can find a proof for it. And there was a parallel postulate that plagued Euclid forever, that he really wanted to prove it, because it was very exciting to him that it gets proven. I don't think it was good. I think we're okay with keeping it a postulate. It works in Euclidean geometry, but not in others. All right, so this is the second postulate. postulate we want to use, which is segment addition postulate. Now these should be obvious. These should be like kind of duh, because we don't pick anything complicated to be a postulate. But what the segment addition postulate says, if you have AC and B is between them on a line here, or a segment, then AB, its distance, plus BC, its distance, equals the distance of the whole thing. So if this was 1, let's say that was 3 and that was 7. So what's the distance between 1 and 3? Now what's the distance between 3 and 7? And what's the distance of the whole thing? 6. So the pieces add up to the whole. So again, it's not like an earth-shattering concept, but we're stating it. Yeah, well, why is it not proving that? Because I guess we couldn't figure out how. And sometimes, because remember, proofs have to be based on things that came before it. And we don't have anything smaller than this that we can base it on. Yeah.
Isn't it kind of syllogism?
Why is this like syllogism? If this is that and that, maybe.
If a postulate or something you're accusing me that something that came before it, then how did somebody find out the first thing?
Well, that's why we made assumptions. So the postulates are not based on anything necessarily that came before it. It could be nothing. So we know about distance, so the idea is to try and build on it if we can. So we're using postulate 1 of it here because we know that distance, and we know that distance to get, adding them together. It basically says you can add distances together to get another distance. So it's building on postulate 1, but it's not what you're trying to say there, I don't think. So that just says, we're going to do a quick example here. I've got D, E, F. If I know this whole thing is 5, and I know this little piece is 3, what's this little piece? 2. Yep. That's the segment addition postulate. All it is. Okay, so here's some examples I have. So if we want to find Km, now here's an important thing here. Notice that a segment designation with no bar on top means we want the measure of the segment. If I want segment Km, I say Km with a little bar on top. If I want the length of Km, right, this is really important and subtle, so please make sure you're listening. Really important. We just say Km with nothing on top. If there's nothing on top, that means I want the length or the distance of that segment. Yes?
It's like a smart aleck proof, so like when you say 5 km, they just don't go like, there it is.
Right. We don't do that. If it says find Km, it's saying find the length of Km. That's what's implied here because there's no bar on top. Find the length of Km. So here's Km. I want this. So what is it? If this piece is 24 and this piece is 12, what's the length of Km? 36. You just add those values together. Length of Km is 36. Looking at this one, UV. UV is this little piece. The whole thing here is 56. This little piece is 45. So how do I find what UV is? Yeah, what do I do, Joseph? Yeah, because let's call this X. X plus 45 equals 56. So subtract that. And I'm just being very explicit here because these are simple ones, but they can get a little harder. Okay, find LM. So I want this one. Well, how am I going to set this thing up? Yeah, Amanda, how am I going to set this up?
X equals 32 minus 3x.
Okay, that's one way of saying, the way I was thinking of it, this is fine. I was thinking of, let's use the addition. What you said was correct too. You said x equals 22 minus 3x?
Yep.
No problem. You see it that way, write it that way. You're fine. It's equivalent.
Equal 4x. So
Yeah.
you just got rid of a step.
All right, so we are going to combine these like terms. And then, so what's x? It's 22 over 4. Let me reduce that fraction. And that's good enough. You don't have to make it into a decimal or anything like that. Just make it 11 halves. Well, oh, and that's x. I'm sorry. Let's go back and read the question. Did I find ln? What did I find? I found x. Is that ln? What's ln? 3x. So I have to do 3 times 11 over 2. And that's 33 halves. And here's my, the answer to the question. Be very careful, which I wasn't just now, to really read the question. Did he find what we were asked to find? Very common to say, I found x, I'm done. And if it says find x, you are done. But if it says find some length, you may have some business to do. If it said find KL, you would be done. And so that's how we do those. And we have some retries. Question? Yeah?
So whenever you put a point down, if you already symbol, you put down, just put the other point.
A letter represents the point, yeah. All right, so do the retries. Let me put up the answers. So I got 42, 14, and 23. Did we get anywhere close? Did we get exactly that? Some people did. Are we getting stuck anywhere? Yeah.
I don't understand that.
F. And you had a question on E? I saw questions on both of these. Basically what you do, and then this one, this plus that equals that. So it's like if we put an X here, and I'm not going to do this one because you got it, but this is really what you were doing in your head. Right? You can kind of do that in your head. You can see it. Now once we start putting variables in it, you don't see it as well. It's the same thing. This piece plus that piece equals whole thing. And then I solve this equation. Okay, 4x equals what? Is that 24? Okay. And so I get x, and then I go back and say, well, they didn't ask me for x. They want BW. BW is x plus 8. 6 plus 8 is 14. Okay, so that was that one. Now let's try and see what happened with f. Same idea. This plus this equals whole thing. So 7x minus 8 plus 3x plus 5 equals 8x plus 9. So I divide my like terms, 7x plus 3x, negative 8 plus 5. I'm going to move that 8x over here, minus, right, and add the 3 over here. So I got 2x equals 12, and then x equals 6. Once again, x was 6. But now what did they ask me to find? ST. So ST is 3x plus 5. I'm pretty sure that the x was 6, and 18 plus 5 is 23. So you had to find the x first, and then you had to plug that in. And I don't know if that's answering your question or not. Does that help? Where are we getting, I'm just curious, like where are we getting a little stumped with this? Did we get this far to know what the equation was?
Yes.
Okay. It was just kind of remembering how to work the equation? Yeah, just remembering the equation stuff, right? Combine your like terms, variables on one side, numbers on the other. Okay, fair enough. And then last little thing I want to talk about here is comparing segments for congruence. Now, do we understand what it means to be congruent? Somebody tell me, what does it mean when things are congruent? What does that mean? They're equal? Is that what it means? Same? No. That's not, well, what? That, no, similar has a different meaning. Now, I know what you're trying to say in English, but in math, similar is something different. Congruent means clone. And we actually have a clone in the room with us, which is kind of awesome. So, twins are clones, right? So, in a sense, you can say Kyle is congruent to his brother. Oh, sorry, I didn't mean to pick on you. But I have other twins, I'm going to pick on them later. So, to be congruent, you're a copy. You have the same size, same measure. This desk, congruent to that desk. Now, are they the same? Are they equal? They're not the same. They're two separate things. He surely isn't the same as his brother, right? They're two separate things. Sorry. It's like, I'm never coming back here again. I've been hoping, you know how long I've been hoping to have identical twins so I could use that in this example. I'm so happy. So anyway, they're clones. So congruence means clones. So if the way I tell if things are congruent, do they have the same size? All right, so that's the way so what I'm going to do is, let's do this. On your paper, go ahead and plot these points. -3 and 4. Now when you plot, always put the letter, and that's J, right? So make sure when you're doing this is our introduction to coordinate geometry. So you have to put those coordinates on here. There's J, where's K? L, M. So we're going to put those on there. can I finish this first? All right, so it wants to know about JK, so I'm going to make that segment, and it wants to know about LM. So I'm kind of drawing these segments in. And how can I tell if they are congruent, right? They're not equal, they're not the same, they're obviously two distinct segments. What is the length of JK? Well, let's see. This one I'm at -3, right? That's the x. And this one, the x is at 2. So what does my rule say? It says you can subtract these two values and take the absolute value. So careful now, it's 2 minus -3, which is what? 2 plus 3, which is 5. Another way to know it's 5, count the boxes. 1, 2, 3, 4, 5, right? Distance between -3 and 2 is 5 units. Now this one, we're looking more at the y values. This one has a y of 3. This one has a y of -2. Same thing, you find distance by subtracting. And I'm going to subtract the other way to show why I need absolute value. So -2 minus 3, that's -5, which is 5. And again, you can count boxes. 1, 2, 3, 4, 5. So are these congruent? Yes. How do you state two segments are congruent? Oops. You say segment JK is congruent. It's an equal with a little squiggle on top to LF. They're congruent lines because they have the same length, or congruent segments rather. Okay, so again, these are basic things, but things we have to know. Oh, can you please not put them on the side? I'm going to trip on them. Yes?
So then we all lines incongruent, then they'll ultimately.
It's an interesting question. Are all lines congruent? Well, it depends on what?
Oh, things congruent?
I don't know. All I know is that if it's something I can define a size, because I can't really, how do I define the size of a line? I can't, right? But I can define the size of a segment. So very often we're going to say segments are congruent, but not lines. All righty, questions?